Alright, so we have a triangular plate supported by a cable at A. That's going to be one force right here. We'll call this tension. And we have a hinge at B. We'll talk about that more in a second. Its weight is 400 pounds and acts at the plate's center of gravity. So that's going to be right here. So the gravitational forces from every single atom of this triangular plate can basically be represented by this 400 pounds at this point right here. In addition, we have a 500-pound load. Here it is right here. And a 200-pound-foot moment along the positive x-axis. So here that is. And just keep in mind, this is a couple moment. They didn't say that explicitly, but remember, a regular moment depends on what point we're calculating it about. So if this was a regular moment, what point is it about? You know, there's no information for that. This is a couple moment. It can act about whatever point you're summing moments about. So if the plate is in equilibrium, find the tension in the cable and the reactions at the hinge. So let's talk about this hinge, the hinge at B. So this hinge at B is clamping on to this point right here. And I'm trying to think about where exactly it clamps. Does it clamp here? Or I'm going to assume that it clamps exactly at this point right here, measured out by this 0.5 feet here. Otherwise, you know, where exactly would this point be, acting? This is the only point where we have a solid measurement, so I'm going to assume it's acting here. So let's say the hinge is acting at this point. So the hinge is gripping at this point, which means the hinge puts a force at this point. And this force, this one force, will have an x component, a y component, and a z component. And these are all unknown, so each one of these here is an assumption on my part. The direction, that is. I know that there will be 3 components for this one force, but the directions here are all assumptions. And here's that force in vector form. Now, I also know that a hinge, in addition to creating one force, a hinge will create at most 2 couple moments. So let's reason through that. Let's just say I put, 2 forces. I took my 2 hands and pushed on the plate in this way, such that we want to kind of rotate in this direction. That hinge will not allow that. So we say that the hinge at point B creates a couple moment in the opposite direction to fight that. So this direction here is the x direction. So we know we'll have a moment from hinge B in the x direction. And I'll just assume, the positive x direction. Now let's say I also try to rotate the plate in this manner. These 2 forces would want to cause a rotation in the z direction. And of course, the hinge would not want to allow this. The hinge would fight against my 2 forces. So in this case, the hinge is putting a moment in the negative z direction to fight against this red rotation that I'm trying to cause. So this is just to go to say that this hinge here will also create a couple moment in the z direction. And just in my picture here, I'm assuming it to be in the negative z direction. That's okay, that direction's just an assumption, but I'll just stick with that, the negative z direction. Now, lastly, pretend for a moment that all these other forces are not here and it's really just the hinge that's here. And let's say I put a force downwards in the negative z direction. Well, that's going to want to cause my hinge to rotate, or my plate to rotate this way about the hinge. Now, this is okay. The hinge will not fight against this. The hinge will allow rotation in the y direction, which means that that hinge creates no couple moment in the y direction to fight against any forces that may cause that plate to rotate in the y direction. So just to make sure we're getting this, just take this random object right here, and let's call this the x direction, and we'll call this the y direction. If this cylinder is sort of spinning around like helicopter blades, that's going to be sort of an angular acceleration vector, a moment vector, torque vector, whatever you want to call it, in the y direction. But if I'm instead spinning like this, like you're unraveling a scroll or something like that, that's going to be a torque moment vector in the positive x direction. Just know that moments, torques, rotations, they have vectors too. So all in all, the total couple moment exerted at B will be this vector right here. Each one of these is just a smaller component of the entire couple moment vector that hinge B exerts onto this plate. So, notice that our only other unknown is the tension in this cable. And the tension in this cable is only going upwards in the z direction. It's only in the z direction, which means it's only one unknown here. So in total, I got 1, 2, 3, 4, 5, 6 unknowns, which is perfect. Because remember, sum of the forces equals 0 gets us 3 equations, x, y, and z. And sum of the moments about some point, that point will be B equals 0, will also get us 3 equations, 6 equations, and we're good. So we'll focus on our forces first. We'll get all of our forces in Cartesian vector form, and we'll just add them together. So let's work on that. So we just have the weight of 400 and this other external force 500 remaining. That's really it. Remember, this thing over here is a couple moment. It's not a force. So that 500-pound force only acts downwards in the z direction. That's it. And the force of our weight, same thing. Only downwards, with a magnitude of 400 in the z direction. So yeah, I'll just add up the x, y, and z components of all my forces equal to 0. So looking at it, if I add all the x components here, the only non-zero one is bx. And the only way for this equation to equal 0 is if bx is equal to 0. And the same thing with all the y components of our forces. So, by must equal 0 as well. So we'll actually have something for our sum of the z force components. So I'll write that out. And we can sum this up to be negative 900. So this will be equation 1. So now we're going to sum the moments about our point B. So we'll start with the moment of our tension vector. So of course I'll need an r vector. So the vector will be from our point about which we're calculating moments to any point on the line of action of the force. I think this one will be the most readily available one here. So r from B to A, cross with our tension vector. Of course we can do the coordinates of A minus the coordinates of B, and that will work fine. But imagine that we started at B and walked towards A. Well, I know we would walk forward 6 in the positive x. We would walk this distance in the negative y direction. That'll be 1.5. And if we walk from B to A, we're not going up or down in the z direction, so that is a 0 in the z. Alright, so we'll just set up our cross product here. Alright, so we'll cover up the x, and we'll get negative 1.5 tz minus 0. We'll cover up the y, and it'll be this product minus 0. And don't forget to put that extra negative on it. And covering up the k, looks like we'll have basically 0 minus 0. So plus 0 in the k. And this whole thing is the moment that our tension causes about that hinge point B. Alright, so here that is up here. So now we'll calculate the moment of this 500 pound force. My R is going to be pretty simple here. I'm just going to go from B to D. And if we travel from B to D, we're really just traveling in the negative y direction, and that's it. So 0x, negative 1.5y, and 0z. And here's my force again. That's just going downwards 500 in the z direction. So now I'll just set up the cross product. So covering the I, we'll just have positive 1.5 times 500 minus 0. So 750, that'll be positive. Covering the j's, 0 times 500 is 0, minus 0 times 0 is just going to be one big 0. And of course, 0 doesn't care if you have a negative or positive on it. So applying that extra negative for the j is meaningless. And covering up the k's, same thing. 0 times 0 minus 0 times negative 1.5, just another big 0. Alright, and this is the moment from that 500 pound force about our hinge point B. Alright, one more to go. The moment of the weight vector. So for the moment of the weight vector, my R vector will be from B to this center of gravity point right here. So if I walk from there to that center of gravity, I'm only moving 2 in the positive x. I'm moving negative 0.5 in the y direction, so 0.5 in the negative y direction. So negative 0.5 the y. And of course I'm not moving up or down in the z. Of course I have the weight vector, just 400 going downwards in the z. And here's the cross product. Covering up I, doing that multiplication, we'll get a positive 200 minus a 0. Covering up the j, we'll get a 2 times negative 400, so negative 800 minus a 0. Alright, so negative 800 comes out of this, but remember, because it's the j, we have to put another negative on it, which ultimately results in a positive 800. And lastly, for z, we'll just get 0 minus 0, basically. So a 0 z component. Alright, so that is our moment of our weight vector about our hinge point. So I'll assemble that, and I'll also won't forget to put that couple moment in vector form as well. We can't forget that. So this couple moment really only looks to be going in the positive x direction. So that's as simple as 200 I hat and 0 for all the rest. And of course I can't forget the couple moments provided by the hinge support itself. I'll just bring those back in. So we're just adding vectors now. We're going to add up all these moment vectors, x, y, and z. Alright, so just take a second and make sure you're okay with all these equations here. We had 6 unknowns in the beginning. We figured out 2. So now we have 4 unknowns, and I spot 1, 2, 3, 4 equations. So we're good. We're still good. And looking at this one, this will be 0 right here. The z component of the couple moment that the hinge creates. Okay, so now we're down to 3 equations and 3 unknowns. And our unknowns are BZ, that tension, and the moment from hinge B in the x direction. And it doesn't look like we need any sophisticated math to solve this. Looking at our equation 3 here, we can figure out TZ. So TZ, which is really just the force in that cable, is just going to be 800 divided by 6, which is 133.3 repeating pounds. And with that, we can plug that into TZ here. We can figure out BZ. So if you do 900 minus 133.3 repeating, you will get 766.6 repeating pounds. And also with TZ, you can plug that in here and figure out your last unknown. If we do that math, we'll get that the moment from hinge B in the x direction will equal negative 950. Of course, the units being pound-feet. Now, when my math gives me a negative, it means that my assumption was incorrect. My assumption was that this component acted in the positive x direction, and the reality is telling me this is in the negative x direction. So I have all of my 6 unknowns right here. Now, if they want the reactions at the hinge, just know that we have to Pythagorean theorem all of my force components. Remember, these are all just the components of the actual one single force that is acting at that point B. But since x and y are 0 here, it's kind of, no need to do that. So the force reaction at the hinge is that 766. Same concept goes for moment. Have to Pythagorean theorem those moment components together, but we have the same thing going on. So the moment reaction at the hinge is that 950 in the negative x direction. And of course I have the tension in the cable, 133. Alright, so in my opinion, the hardest part is just setting up the problem, navigating this hinge support, where are the moments going to be, how does it act? And then it's just, doing your R cross F, putting your forces in Cartesian form, and summing up those force and moment vectors. So I hope it made sense. If you have any questions, feel free to post them in the comments.